computer science lab, and welcome back to quantum mechanics. Unfortunately, this is the final lecture. Today, we're going to be talking about perturbation theory. Now, I discussed this a little bit last time, but very few Schrodinger equations can actually be analytically solved, as in you can't get an exact solution to most of them. You can describe the entire universe in quantum mechanics as long as the entire universe you're speaking of is what the? Oh, it's just a spider. A proton surrounded by an electron. I wonder if he's curious about mathematics. No, don't kill it. No. Why would you do that? Aw. Okay, we'll move on. Dad, he was learning. So, if your universe looks like this, congratulations. You can be described by quantum mechanics. Now, uncongratulations because you're just a hydrogen atom. You probably can't understand the words that I'm saying. The entire universe is not a hydrogen atom in isolation, which means that, we have to make approximations. But how? There are lots of ways to approximate things. And we're going to have to come up with a special one for quantum mechanics in specific. So what do? It's time to talk about perturbation theory. Let's say we have a potential that is well understood. And this potential is associated with a Hamiltonian for which the Schrodinger equation can be solved analytically. Let's call that Hamiltonian H naught, and all of these initial ones psi naught, just to emphasize that these are the initials. Now, let's say we make a small perturbation. Let's call this perturbation lambda h prime. Yes, this is kind of a technique stolen from calculus of variations. It does not matter. So, the new Hamiltonian is no longer h naught, it's h, which we're going to take to be h naught plus lambda h prime. So, what does this Hamiltonian do? How can we now find a new solution in the new energy that satisfies h psi is equal to E psi? How? Well, it's time to introduce power series. Hopefully you already know what power series are, but it's time to introduce them in this context. We're going to say psi over here is the initial psi plus a power series of lambda. So let's say n is equal to 1 to infinity of lambda to the n times some correction psi naught n, or let's say just psi n. So if, lambda is a very, very small number, these corrections are going to get smaller and smaller and smaller. In practice, it's only really useful to study the first two corrections. Now, of course, if the wave function changes, the energy levels are going to change with them. So we now have E is equal to E naught plus the sum from n equals 1 to infinity of lambda to the n En. Now, things are looking pretty easy so far. But here's what we're going to do. Let's take this and, plug it back into there. What do we get? Well, we get, H is equal to H naught plus lambda H prime, right? So, of course, flipping this on its head, h naught is just h minus lambda h prime. So, if you plug that in, you get h minus lambda h prime. Then you get the initial wave function is just psi minus this. And similarly, this is going to be equal to E naught, which is this minus this, times psi, which looks like psi minus the sum up from n equals 1 to infinity of lambda n psi n. So with this, can I look? Oh, sorry. So we set this to psi n naught lambda to the n from n equals 0 to infinity, and we also set this to e n naught lambda n from n equals 0 to infinity. When we do this multiplication and we plug back in, this is useless at first. All it's doing is overcomplicating things. But now, what happens when we take the dot product of both sides with, well, not dot product, the inner product, which, if you recall, the inner product of these two is just going to be the integral of their product. And of course, recall that two functions or operators with zero inner product are considered orthogonal. You get four terms. So taking the dot product on all sides, of course, what's going to be on the other side of all of these terms is going to be psi naught, because that's what we're taking the dot product with. What's going to be on the other side is, well, this is where the lambda comes into play. We actually don't know yet. What happens is that we can take this and expand it into a power series expression. This is the entire reason we decided to use lambda. Anything with lambda to the 0 has to be associated with thing on the other side with lambda to the 0. In this case, the term with lambda to the 0 is h naught psi naught is equal to e naught psi naught. So this is telling us nothing new because it's just the original assumption. Of course, that changes when you go to the lambda to the first term and the lambda to the second term, but I already forgot what that was. We get h naught psi naught plus h prime psi 1 is equal to e naught psi 1 plus e1 psi naught. So this tells us that h naught psi naught plus h prime psi 1 has to be equal to e naught psi 1 plus e1 psi naught. So things are relatively simple. Now when we take the dot product of both sides, well, not the dot product, the inner product of both sides with psi naught, what do we get? Well, first of all, consider that psi naught's dot product with itself has to be 1 as it's normalized. Since it's a wave function, that must mean that its norm squared is going to be equal to 1. So we get that when we take the dot product of both sides, we have, well, this is actually the important part. You can't take the dot product from this side. We're going to take it from this way. Psi naught h naught is psi naught plus psi naught h bar psi 1 is equal to psi naught e naught psi 1 plus psi naught e1 psi naught. Consider that e naught and e1 are scalars. So, erasing this, since e naught and e1 are scalars, we can just take them out of the inner product, since the inner product is an integral after all, and integrals are linear, which gives us psi naught h naught psi naught plus psi naught h prime psi 1 is equal to e naught psi naught psi 1 plus e1 psi naught psi naught psi naught.